Hello, welcome to RCC's Math Tape 093, solving 2x2 linear systems of equations by the addition method. On this tape, 2x2 systems will be continued, and in the next tape we will cover 3x3 systems. The addition method will be used both times, and so you need to learn very well what is on this tape. As you go through the material, take notes carefully, make sure they're exactly right. Mark on your paper any places you don't understand so you can ask for help when you get to the lab to work with a lab instructor or a tutor. Also, in the exercises that I give you, if you don't understand any of the problems, or if you make mistakes that you cannot find, mark those as well for the same purpose. Now let's begin. Our objective on this tape is to solve 2x2 systems of linear equations by the addition method. Solve 2x2 systems of linear equations by the addition method. Prior to this tape, you should have been working with solving 2x2 systems of linear equations by graphing and by the substitution method. Each of those is a rather specialized method. Graphing works beautifully when the equations are equations that can easily be graphed and when the solution is integers. The substitution method is ideal when it is easy to get one of the letters in the equation by itself. The addition method is a more general method which you will find you use more than the other two put together. I'm going to begin by giving you the procedure for the addition method. This is rather lengthy, and so write it down carefully. Be sure you get all the details right. The procedure for solving by the addition method begins with step 1, multiply each equation by some real number. Multiply each equation by some real number chosen to make the coefficients of one of the variables be opposites. Multiply each equation by some real number chosen to make the coefficients of one of the variables be opposites. In almost every case, you will choose different real numbers for the two equations. One real number will be multiplied by the first equation, a different real number by the second equation. The numbers that you choose are chosen to make the coefficients of one of the variables be opposites. You might choose the variable y and make the coefficients of y's be opposites. Or you might choose the variable x and make the coefficients of the x terms be opposites. Remember that opposites are numbers that have the same absolute value but opposite signs, like 2 and negative 2. Step 2, this gives the method its name. Add the two equations. Add the two equations and solve for the variable that remains. Add the two equations and solve for the variable that remains. Since in step 1 we made the coefficients of one of the variables be opposites, when we add the two equations, that variable will disappear and will be down to a single variable. You are to solve for the variable that remains. Step 3, back substitute to find the value of the other variable. Back substitute to find the value of the other variable. You remember from working the substitution method that the term back substitute means to choose an equation that has the variable you have just found the value for and the other variable. Any equation in the system, all of the work that you're doing that has this set up will do. Any equation that has both the variable you just found and the other variable. You substitute in the value that you just found and find the value of the other variable. Now you will have solved for both of the variables, and so the only thing that is left is check in both original equations. Check in both original equations. Now let's look at examples. Example 1 is the system 4x plus y equals 2. 3x plus y equals -1. We're solving by the addition method. We must multiply each equation by some real number chosen to make the coefficients of one of the variables be opposites. Notice that with the variable x, the coefficients are 4 and 3. 4 and 3 certainly are not opposites of each other, but we could create a coefficient that is like a common denominator. If you had fractions with denominators of 4 and 3, the common denominator you would choose would be 12. And so we can multiply the top equation by 3 to get 12x, and so on across. We can multiply the bottom equation by 4 to get 12x, and so on across. And we would choose one or the other of them to be negative so that we would have opposites, so that we could create, for instance, 12x in the first equation and negative 12x in the second equation. And so multiplying the top equation by 3 and the bottom equation by -4 would do what we're asked to do. Now let's consider the y. In the first equation, the y has an understood coefficient of 1. In the second equation, the y has an understood coefficient of 1. They are not opposites of each other, but if you multiply either of these equations by -1, you would create opposite coefficients. You could multiply the first equation by -1 to get -1y, and leave the second equation as it is, that is, multiply by +1 to get +1y, or vice versa. I'm going to choose to multiply the second equation by -1. And so out beside the brace that indicates the system of equations, I'm going to put the multiplier for each of these equations. For the first equation, our multiplier is simply 1. For the second equation, our multiplier is -1. Now I'll have 1 times 4x plus y equals 2, which gives me 4x plus y equals 2. -1 times 3x plus y equals -1, which gives me -3x minus y equals +1. Notice that we have now set it up so that the y coefficients are opposites of each other. One reminder, when you're multiplying the equation by the number, don't forget the golden rule. Do unto the right what you do unto the left. If you multiply the left-hand side by -1, you must multiply the right-hand side by -1 also. Now that we have the equation set up as our first step in the addition method requires, we're ready to add the two equations. If we add 4x and -3x, we get x. The y's will cancel. 2 plus 1 is 3. And so we've got x equals 3. Well, this is the answer for x. We've got the value for x now. Now we will back substitute into one of the equations that has both x and y. Notice that if we look just up above this answer, the last equation we had written before it has both x and y. So does the one above it. So do the originals. We can choose any of these that we want to for our back substitution. Anything in this group will do. I have chosen to use the first equation, 4x plus y equals 2. I've chosen it because there's no real advantage to choosing anything else. The coefficient of y, which is what I'm going to be solving for, is 1, which is as easy as it can possibly be. And it will be easy to work with this equation where all the coefficients and constants happen to be positive.